There's a simple formula in astrobiology: where there's water, there could be life. It's no surprise then that the discovery of extraterrestrial worlds rich in water is one of the most exciting chapters in modern space exploration. Recent breakthroughs have revealed a growing list of exoplanets, planets beyond our solar system, that may host vast oceans beneath their clouds. Among these are intriguing candidates like the super-Earth TOI 1452b, and perhaps even more astonishing, K2-18b, which might hold the first detectable biosignature outside Earth. Let's dive into these remarkable discoveries, how scientists are detecting alien water from light years away, and whether we're finally on the edge of answering the age-old question: are we alone in the universe? Although the search for exoplanets only began in earnest in the early 1990s, it has quickly grown into one of the most exciting fields in astronomy. Since the first confirmed exoplanet orbiting a pulsar, PSR B1257+12, scientists have now catalogued over 6,900 exoplanets, ranging from massive gas giants to Earth-like rocky worlds. Yet among this galactic zoo, a special type of planet has captured the imagination of researchers: ocean worlds, planets covered in deep, global seas, possibly teeming with life. These watery realms might even outnumber rocky planets in the universe. One of the most promising discoveries in this category is the exoplanet TOI 1452b, located about 100 light-years away in the constellation Draco. It orbits a binary star system and was discovered using data from NASA's TESS, Transiting Exoplanet Survey satellite. The planet was found because of regular dimming in its host star's light, a telltale sign of a planetary transit. To investigate further, researchers from the University of Montreal, led by Charles Cadieux, used ground-based telescopes including the Montmegantic Observatory and the Canada-France-Hawaii telescope equipped with a SPIRO spectrometer. What they found was compelling. TOI 1452b is what astronomers call a super-Earth, a planet with a mass between Earth's and Uranus's. It weighs about 4.8 times the mass of Earth and is 1.6 times larger in radius. However, the real surprise came from its density, just 5.6 grams per cubic centimeter. This is surprisingly low for a rocky planet of its size. Typically, such planets have dense iron cores and thick rocky crusts, which give them a much higher overall density. So, what's going on with TOI 1452b? While TOI 1452b is a compelling candidate, another planet has already provided concrete evidence of water, GJ 9827d. This exoplanet orbits a Sun-like star just 97 light-years away and is part of a multi-planet system. Led by Pierre-Alexis Roy, a research team again from the University of Montreal used the Hubble Space Telescope to observe GJ 9827d's atmosphere as it passed in front of its star, a technique known as transmission spectroscopy. The result? A distinct absorption line at 1.4 microns, a clear sign of water vapor in the atmosphere. While it's theoretically possible the data could be explained by a hydrogen-helium envelope with a few water molecules, other aspects of the spectrum suggest something richer and wetter. Crucially, this planet is not young, it's about 6 billion years old, and orbits very close to its star, meaning its lighter gases should have long since been stripped away by stellar radiation. This implies that what remains is likely a water-rich atmosphere, perhaps the remnant of a once icy world that migrated inward, much like some of Jupiter's moons might have if they'd fallen toward the Sun. While Hubble provided the first hints, it's the James Webb Space Telescope, JWST, that is poised to revolutionize our understanding of alien water, and possibly even alien life. Webb's powerful infrared instruments can detect molecular signatures in exoplanet atmospheres with incredible sensitivity. This includes not just water vapor, but potential biosignatures, chemical compounds that could indicate life. K2-18b is a planet about 8.6 times the mass of Earth, located in the habitable zone of its red dwarf star. In 2023, JWST detected dimethyl sulfide, DMS, in its atmosphere, a sulfur-based molecule that, on Earth, is produced exclusively by life, specifically marine plankton and during the decay of organic matter. This could be the first detection of a biosignature outside Earth. However, scientists are urging caution. The DMS signal in the Webb data overlaps significantly with methane, making it difficult to isolate. While both molecules can be produced biologically, they can also arise from geological or chemical processes. More detailed data is needed before anyone can declare that we found alien life. Fortunately, JWST's mid-infrared instrument, MIRI, is capable of separating these signals more clearly in future observations. If DMS and its breakdown products can be confirmed, and methane ruled out as the source, this would be a monumental breakthrough in the search for life. The exciting thing about all of these discoveries is that we're only just getting started. Missions like JWST, Ariel, and future ground-based telescopes like the Extremely Large Telescope, ELT, will continue to peel back the layers of exoplanet atmospheres, scanning for water, oxygen, methane, DMS, and other signs of life. Planets like TOI 1452b, GJ 9827d, and K2-18b are at the frontier of this search, places where oceans may lap against alien shores and molecules associated with life drift through strange skies. Whether we are witnessing the early signs of life beyond Earth, or just learning more about the astonishing variety of planets in the galaxy, one thing is clear: the universe is wetter, weirder, and more wonderful than we ever imagined. The implications of these discoveries go far beyond the mere presence of water. In astrobiology, water is the universal solvent, an essential ingredient for life as we know it. Its ability to dissolve a wide range of substances makes it the ideal medium for biochemical reactions. The discovery of exoplanets like TOI 1452b, GJ 9827d, and K2-18b, each showing signs of liquid water or water-rich atmospheres, opens an entirely new chapter in our understanding of potentially habitable environments beyond Earth. Let's take a step back and consider the broader context. Out of nearly 7,000 confirmed exoplanets, only a small fraction reside in the so-called habitable zone, that sweet spot around a star where temperatures allow water to remain in liquid form. Even fewer of those have the right combination of size, atmosphere, and composition to suggest the presence of water. And yet, the fact that we're already finding so many promising candidates strongly hints that water worlds may be more common than we once believed. The James Webb Space Telescope, with its ultra-sensitive instruments and high-resolution infrared capability, is ushering in a golden age of exoplanet research. For the first time in history, we're not just detecting exoplanets, we're studying their atmospheres, measuring their chemical compositions, and peering into the possibilities of alien biospheres. Webb's detection of molecules like methane, carbon dioxide, and even dimethyl sulfide, DMS, in the atmosphere of K2-18b might be just the beginning. K2-18b, in particular, is an incredibly fascinating case. It lies within the habitable zone of its red dwarf star and has a thick hydrogen-rich atmosphere. If the detection of DMS turns out to be accurate, it could represent the first credible evidence of life beyond Earth. Why? Because on our planet, DMS is only produced by living organisms, specifically marine plankton and other microorganisms. There are no known abiotic processes that generate it in significant quantities. So, finding it on K2-18b, even in trace amounts, would be revolutionary. Of course, the scientific community remains cautious. Extraordinary claims require extraordinary evidence, and the faint DMS signal detected by Webb still needs further confirmation. But the tantalizing possibility is enough to energize researchers and spark new missions and studies. More follow-up observations with Webb's MIRI instrument are planned, targeting the mid-infrared range where DMS and other organics leave their most distinct fingerprints. Meanwhile, theoretical models are evolving just as fast. Scientists are developing complex simulations to understand how such ocean planets form, migrate, and evolve over billions of years. Some suggest that water worlds like TOI 1452b could have deep oceans extending hundreds of kilometers below the surface, with high-pressure ice layers at the bottom and possibly even hydrothermal activity, just like the vents found on Earth's ocean floors, which are teeming with life. These hydrothermal vents may be key. On Earth, they host ecosystems that thrive without sunlight, relying instead on chemical energy from the planet's interior. If similar processes occur on water worlds, life could exist even in the absence of light, deep beneath an icy crust or thick atmosphere. This broadens our definition of habitability far beyond traditional Earth-like conditions. Thanks for watching Space Lab, where the universe comes to life.